Today I want to go back and revisit section 2.4 with the chain rule. In particular, I want to work with the derivatives of bases other than e and the log derivatives. As you recall, I gave you the rules, and you can remember those rules by all means if that's something that you can do. I personally don't. I always have to go back and look at the rules because it just doesn't stick in my mind. What I use is implicit differentiation, which we've talked about in section 2.5 here. So what I want to do is go back and rework those problems and show you how that I do them and using that implicit differentiation. So in example 1 here we have the derivative. We're going to derive f of x equals 5 to the x. So what I do is I change my f of x to y. And so we have y equals 5 to the x. What I can do is I can take the natural log of both sides. And again, we saw that back in the previous sections, or in the previous lessons. So we have the natural log of y equals the natural log of 5 to the x. We can go ahead and take this x and bring it to the front, so we have x natural logs of 5. I can go ahead and find the derivative. Derivative of natural log of y, it would be 1 over y dy dx. And that's going to equal the derivative of x natural log of 5. Well, natural log of 5 is a constant, so we just have the natural log of 5 as our derivative. We can go ahead and multiply our y over, so dy dx is going to equal the natural log of 5 times y, but we know that y is 5 to the x. And you can rewrite that if you want, or we can leave it just like the natural log of 5 times 5 to the x, which it goes along with the rule, of course. We have the derivative of a to the x, or a constant to a variable, is the natural log of the constant times a to that variable, or the function that we're looking at. So here we did that, natural log of 5 times the original function, 5 to the x. So again, it's a little more work, but you don't have to remember the rules because we've done implicit differentiation and we've worked extensively with that. So I'm going to run through several problems. You don't have to watch through all of them, I suppose, but it might be something that you get something out of, maybe make your life a little easier. So here we have, I'm going to go ahead and take the natural log of y equals the natural log of 5, and then our 2x plus 6 is going to come down. We can put it in the front, or we can just multiply it out, doesn't matter. Our derivative, so we have 1 over y dy dx, is going to equal the derivative here. Well, we have natural log of 5, that's a constant, so we're just looking at the derivative of 2x plus 6 times that natural log of 5. So we have the natural log of 5 times 2. If I multiply my y over, dy dx is going to equal my y, which is 5 to the 2x plus 6 times the natural log of 5 times 2. And we'll put it in parentheses there. And again, it goes with that rule. If you recall the rule there, we have the derivative of a constant to a function now. Remember u as a function. We have the natural log of the constant, so we have the natural log of 5. We have the function itself, 5 to the 2x plus 6, and then we take the derivative of the function, of the exponent. So the derivative of 2x plus 6 gives us the 2. So again, we can remember the rule, or if we do logarithmic differentiation, it becomes just as easy, in my opinion. Well, what happens with a log? If I have log base 7 of 3x minus 1, how do I tackle that problem? Nope, I guess we should equal this to a function f of x. So again, we can let y equal log base 7 of 3x minus 1. I can change this into an exponential function. So we have 7 to the y equals 3x minus 1. Now, I can take the natural log of both sides to get that variable out. So I've got y, natural log of 7, equals the natural log of 3x minus 1. I'm going to go now and find the derivative of my y natural log of 7. Natural log of 7 again is a constant, so we have the natural log of 7 times the derivative of y, which is dy dx. And that's going to equal the derivative of the natural log of 3x minus 1. Remember, derivatives of natural logs, we take the derivative of the function divided by the function. So we have 3 over 3x minus 1. We're going to divide by the natural log of 7. So dy dx is going to equal 3 over 3x minus 1 times the natural log of 7. And again, if you recall, that's going to be also what we did within our function, or within our rules. So we have log base a of u, which is what we have here. Kind of split the screen there. So we took 1 divided by the natural log of a. A was the base, so we have natural log of 7, that's our base. We have u, which we're taking the derivative of, or the log of, so it's our 3x minus 1, and then times the derivative of what we took the log of. So the derivative of 3x minus 1 was our 3. So we could put 1 over this times 3, or 3 times 1 gives us the 3. In example 4 here, we could expand this out if you want it, or we could go ahead and change that to an exponential as well. So we'd have 4 to the y equals x minus 1 over x. What we can do from here, take the natural log of both sides. So we have y natural logs of 4 is going to equal the natural log of x minus 1 over x. Expand out the right side there. So we have y natural logs of 4 is going to equal the natural log of x minus 1 minus the natural log of x. Go ahead and find our derivative. Derivative of y natural logs of 4 is going to be the natural log of 4 times dy dx. And that's going to equal 1 over x minus 1 minus 1 over x. I can then go ahead and divide my natural log of 4 over. So dy dx is going to equal 1 over the natural log of 4 times 1 over x minus 1 minus 1 over x. And you could go ahead and find a common denominator if you want. Simplify it however you want to look at it. We've done that before, so I won't bore you with that now. I have one last problem here. We have the derivative of f of x equals 3 logs base 2 of x over x. So this one becomes a little more complicated because we don't have just a log. We actually have a chain rule, or a quotient rule there. Sorry, a quotient rule. What I'd like to do is go ahead and get rid of that log base 2 of x and change it into natural logs. And we're going to see that's going to become a lot easier to do this problem. So I'm going to let a equal log base 2 of x. Arbitrary variable, doesn't matter what we let it be. Could be b, could be a, c, z, doesn't matter. What I want to do though is to get this into logarithmic form, in a natural log form. So I'm going to change it to exponential, so I have 2 to the a equals my x. I'm going to take the natural log of both sides, so the natural log of 2 to the a, so my a is going to come to the front, is going to equal the natural log of x. I'm going to divide by the natural log of 2 to get my a by itself again. So I have the natural log of x over the natural log of 2. So I know that a was log base 2 of x, and a is also equal to the natural log of x over the natural log of 2. So I can change this log base 2 into the natural log of x over the natural log of 2. Now you're probably looking at that and saying, well, why do I want to do that? That kind of looks more ugly. And it kind of is at this point, but we have a fraction over a fraction, so we can multiply by the reciprocal, and we're going to rewrite this as 3 natural logs of x over x natural log of 2. Our 3 and our natural log of 2, they're being multiplied both to this, so I can bring that out. So I have 3 natural logs, or 3 over the natural log of 2 times the natural log of x over x. Now I'm in a form that I'm ready to find the derivative of natural log of x over x. So my y prime, or dy dx, or f prime of x, is going to be 3 over the natural log of 2 times the derivative of natural log of x over x. So I have my x times 1 over x minus the natural log of x times 1 over x squared. So my derivative, cleaned up, we're going to have 3 over the natural log of 2 times x times 1 over x is 1 minus the natural log of x over x squared. And that's going to be our derivative. Again, you could manipulate this a little bit if you want, but it gives you a kind of an idea of why we can use, or how implicit differentiation with logs is a little easier possibly, and makes your life a little nicer, and we don't have to remember those complex rules on how to find the derivative of a base other than e or of logs. So if you have any questions, ask and we'll get through it. Good luck and have fun with it.